Hello and welcome to the Epoxy channel. In this channel we often explore epoxy and resin related topics. Today we're gonna continue our discussion about polyurea resin. This is the second video in this topic and I hope you enjoy. While polyurea is a high performance material, it does come with several practical limitations that formulators and applicators must consider. First is isocyanate components are extremely reactive with moisture. Even atmospheric humidity can be crucial. If not stored properly, these can lead to unwanted side reactions, forming carbon dioxide bubbles and solid urea particles that compromise coating integrity. Second, application isn't straightforward as rolling on a paint. Polyurea requires plural component spray equipment that can heat and pressurize each part separately before precise mixing at a spray gun. This specialized equipment can be expensive and need regular maintenance. The part life of polyurea is extremely short, often just a few seconds. That's virtually no room for errors in mixing reactions or application timing. Any imbalance can result in poor cure, foaming, or weak mechanical properties. Next, proper surface preparation is also non-negotiable. Without appropriate cleaning, profiling, and priming, even the best formulated polyurea will struggle to adhere, especially to smooth and contaminated surfaces. Aromatic polyureas, while cost-effective and widely used, suffer from UV instability. They tend to yellow and degrade under sunlight, making them unusable for exposed decorative application without protective aliphatic top coats. Additionally, the material cost of polyurea system is generally higher than polyurethane or epoxy coatings. This makes it more suitable for application where its superior performance justifies the investment. Finally, the learning curve is steep. Spraying polyurea demands trained personnel with experience in handling high pressure systems and reacting systems safely and accurately. So polyurea offers impressive advantages, but realizing its full potential requires careful formulation, equipment investment, and technical expertise. Now that we have covered the fundamentals, it is time to dive deeper into formulation. In this section, we will explore how polyurea systems are designed, what components are used, and how tuning the chemistry affects the performance. Let's take a closer look at what goes into making a high-performance polyurea. Polyurea systems are typically formulated as two-component systems, part A and part B. The A side contains the isocyanate component, which can be aromatic or aliphatic. For better processing and more controlled reactivity, MDI-based polymers are commonly used instead of pure MDI. The B side is a blend of amine-terminated resins. These often include polyetheramines such as Jeffamine D2000 or T5000, which determine the backbone flexibility. Fast-reacting aromatic diamides like DETDA or diethylene toluenediamine are often used as a chain extender to enhance curing speed and mechanical properties. To tailor performance and reduce cost, formulator may include fillers, pigments, and specialized additives such as UV stabilizers for outdoor durability, deformers to minimize entrapped air, and thixotropes to control sag and flow. Balancing these components is a key to achieving the desired performance profile, whether it's flexibility, hardness, or chemical resistance. Processing polyurea systems requires special equipment due to the speed and sensitivity of the reaction. Typically, plural component spray machines are used. This system is independently heat and pressurize the two components before mixing them at the spray gun nozzle. Both the isocyanate and amine components are usually heated to around 60 to 70 centigrades and spray at pressure ranging from 120 to 210 bars to ensure proper atomization and mixing. Successful application depends heavily on surface preparation. The substrate must be dry, clean, and often primed with either epoxy or polyurethane-based primers to enhance adhesion. Additionally, surface roughness helps promote mechanical interlocking, especially on concrete or metals. Finally, the system's reactivity can be finely tuned by modifying the amine structures or adjusting the isocyanate index, providing formulators with great flexibility in tailoring the performance. As shown in the figure, Polyurea application relies on highly specialized plural component spray machines. These systems are engineered to deliver both the isocyanate and amine components under extreme conditions, typically at pressures ranging from 120 to 210 bars and temperatures between 65 to 80 degrees centigrade. Due to the fast reactivity of polyurea, precise control of temperature, pressure, and mixing is crucial, which is why these machines are equipped with integrated systems, including a combustion engine, an electric generator, and an air compressor. The complexity and robustness of the spraying device ensures proper atomization and mixing at the spray tip, allowing the formulation to react instantly and form a uniform, defect-free coating on the substrates. What you see here is a plural component spray machine, the essential equipment used to apply polyurea systems. Due to the externally fast reactivity of polyurea, often curing within seconds, the machine must accurately heat, pressurize, and mix two components, the isocyanate or part A and the amine resin blend part B, right before spraying. These machines typically heat both components to 60 to 80 centigrades and maintain high pressure, often between 120 and 210, to ensure proper atomization and mixing. The device often comes as a self-contained unit equipped with a combustion engine, electric generator, and air compressor, making it suitable for both on-site and remote applications. Such precision and power are critical because even a minor imbalance in temperature or pressure can affect the coating quality, adhesion, and mechanical performance of the polyurea system. In this slide, we're comparing the performance of three common coating technologies: polyurea, polyurethane, and epoxy, each with distinct strengths and weaknesses depending on the application. Starting with cure speed, polyurea stands out with the fastest reaction time, often curing in seconds, which makes it ideal for rapid returning projects. Polyurethane cures more slowly, typically within minutes to hours, while epoxies are the slowest, often requiring several hours or even days for full cure, especially at lower temperature. In terms of application methods, polyurea is mostly applied via plural component spray systems, but some modified systems allow brush application for small areas. Polyurethane is also typically sprayed, but can be rolled or brushed in less reactive formulations. Epoxies are commonly applied by brush or roller due to their longer pot life and high viscosity. When it comes to flexibility, polyurea again leads with excellent elongation and tear resistance, often exceeding 400%. Polyurethane offers good flexibility depending on the formulation, while epoxy systems are generally rigid and brittle unless modified. On abrasion resistance, the polyurea performs exceptionally well, making it ideal for industrial floors and track liners. Polyurethanes provide decent durability, and epoxies, though hard, are more prone to chipping under abrasive forces. Chemical resistance is another important property. Epoxies and polyurea both show high resistance to many solvents, fuels, and acids. Polyurethane is moderately resistant but can degrade under harsh chemical exposure, especially under alkaline conditions. Moisture tolerance during application is a significant differentiator. Polyurea cures well even in humid or damp environments. Polyurethane is moderately sensitive to moisture, and epoxies can suffer from amine blush, foaming, or adhesion failure when exposed to moisture during applications. For UV resistance, aliphatic polyurea performs well and resists yellowing. Polyurethane generally offers better UV resistance than epoxies, which tend to degrade or chalk without a protective topcoat. Finally, considering cost, polyurea is usually the most expensive due to its specialized raw materials, equipment, and skilled labor requirements. Polyurethanes are more moderately priced. And epoxies are often the most economical, particularly in application where speed and flexibility are not critical. All in all, while polyurea excels in speed, flexibility, and durability, polyurethane offers a balanced performance for many industrial and architectural applications. And epoxies are preferred where hardness, chemical resistance, and cost efficiency are key. To ensure a polyurea system performs reliably in the field, it must undergo a series of standardized tests that evaluate its mechanical, thermal, chemical, and environmental durability. We begin with the gel time and reactivity profiling, which helps formulators understand the curing speed and working time, a critical factor in high-speed spray applications. Tensile and tear strains are evaluated using ASTM D420 and D624, respectively. These tests reveal how well the cured polyurea can withstand stretching and tearing forces, both important in applications exposed to mechanical stress or dynamic loads. Elongation is measured to assess the material's flexibility. Many polyurea systems stretch well over 400%, making them ideal for expansion joint, membranes, and areas prone to movement or vibration. Shore hardness, measured via ASTM D2214, determines the surface hardness of the cured film. Polyurea systems can vary from flexible shore A grades to rigid shore D levels depending on the formulation. Abrasion resistance is tested using the Tabor abrasion method, ASTM D4060, which simulates wear and helps predict longevity in high traffic or industrial environments. For chemical resistance, ASTM D543 is applied, where samples are exposed to acids, bases, oils, or solvents to ensure the coatings won't degrade under chemical exposure. Adhesion strength is tested using the pull-off method, ASTM D4541, where the bond strength between the polyurea and substrate is measured. It's an essential parameter for coating exposed to shear or peeling forces. Thermal aging and UV resistance are also evaluated to ensure the system retains performance during under long-term heat or sunlight exposure, particularly important for coatings for exterior structures or desert environments. Lastly, water absorption, measured using ASTM D570, indicates how much moisture the system takes up. It's critical for weatherproofing applications where long-term exposure to humidity or standing water is expected. Together, these tests provide a full profile of the polyurea system, helping manufacturers, applicators, and clients ensure the right product is selected for the right job. In a typical polyurea system, two main components known as the A side and B side are combined at the spray nozzle to initiate the rapid curing reaction. The A side is the isocyanate component, usually composed of MDI-based prepolymers or quasi-polymers. These are formed by partially reaction methylene diphenyl diisocyanide or MDI with small amounts of polyether polyols or amines. This prepolymer format reduces volatility and allows for better control over reactivity. Manufacturers can either source these ready-made or synthesize them in-house for more tailored performance. The B side is the amine-terminated resin blend, which contains the reactive components that drive the fast gel time characteristics of polyurea. Common ingredients here include polyetheramines such as gefamine D2000 or T5000 for flexibility and elongation, and aromatic diamines like DETDA or E100 that serve as chain extenders and help achieve high mechanical strengths. This site also includes a range of additives such as pigments for color, thixotropes for gas resistance, fillers for cost and performance balance, UV stabilizer to enhance weatherability, and 5 surfactants for improved flow and wetting. Together, the A and B components create a high versatile system that can be customized for coatings, linings, membranes, and more. The A side of Polyurea system primarily consists of isocyanate prepolymers, most commonly based on pure or polymeric MDI, that's methylene diphenyl diisocyanate. To fine-tune viscosity and reactivity, MDI is reacted with small amounts of polyether polyols or even amine compounds, forming a prepolymer or quasi-prepolymer. The manufacturing process typically involves controlled heating under a nitrogen atmosphere, usually between 16 and 80 centigrades, to prevent oxidation and moisture intrusion. The reaction between the isocyanate groups and hydroxyl groups or amine groups must be carefully monitored to achieve the desired NCO content, which directly influences reactivity and shelf life. This is usually measured by titration or FDIR spectroscopy. Once the desired properties are achieved, volatiles are removed under vacuum if necessary, and the final product is packaged in moisture-free containers, often under nitrogen. Since isocyanates are highly sensitive to water, even trace amounts can lead to side reactions and gas formation. While solvents are rarely used in modern formulations due to environmental and performance reasons, the process must remain tightly controlled to ensure long-term stability and consistent performance of the final polyurea system. When it comes to manufacturing the B-side of polyurea system, precision and environmental control are key, especially due to the moisture sensitivity of polyethyramines like gefamines. Equipment involved typically includes heated reactors operating in the range of 20 to 90 centigrades, which facilitate homogeneous mixing of resin components. These reactors are often equipped with vacuum systems for degassing and low shear mixers to prevent premature reactions or shear degradation. If the formulation includes filler or pigments, dispersion equipment such as high-speed mixers or bead mills may be used to achieve uniform particle distribution. The finished resin is stored in nitrogen blanket tanks or sealed drums to prevent atmospheric moisture uptake. The manufacturing process begins by bleaching amine-terminated polyether resins such as gefamine D2000 or T5000 with aromatic diamides like DETDA. Next, additives and fillers are introduced and carefully dispersed under controlled shear or to ensure proper incorporation without including air or moisture. Throughout the entire process, moisture control is absolutely critical. Isocyanate used in the A side react volatilely by water, forming unwanted urea linkage and CO2 gas, which can lead to formation of foams, defects, or poor mechanical properties. Therefore, hygroscopic materials like jaffamines must be handled with special care, stored in dry conditions, and often under a nitrogen blanket. Once blended and degassed, the B-side resin is packaged in sealed, moisture barrier containers, ensuring stability and performance during storage and shipment.
Now this is time to end this session, and I hope you enjoy. Stay tuned for the next slides on this fascinating topic. Thank you.